Welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Josef Rukavicka from the Czech Technical University in Prague, and he is going to speak to us about the Restivo Salemi property for alpha power-free languages with alpha greater than or equal to 5 and k greater than or equal to 3 letters.
Thank you for the introduction. I'm happy to be here again in this seminar, in these talks. So let us start with some basic definitions. I'm not sure how many of you are familiar with powers. So I will present also the very basic definitions. I'll start with alphabet. I consider a finite alphabet with Q letters, some set of symbols. A finite word is a sequence of the letters from the given alphabet. Yeah, the sequence is finite in this case. I think this is clear. Yeah. Right infinite words. So we are not considering only finite words. We are considering also infinite words and not only infinite word, but also right, left, and by be infinite. So the right infinite word is an infinite sequence of the letters from the alphabet. So it can be also presented as a mapping between natural numbers into the alphabet. This is also the case in some papers. You can see the function from the natural numbers into alphabet, but also the presentation in this way, like a sequence. So as I announced, there is also left infinite word. Basically, it's the same. It is also a mapping between natural numbers and the letters from the alphabet, but it is presented in this way that it's a sequence which is going from the starting point to the left to the infinity. Yeah, for many results, the difference is not that important, but for my paper, it is important to distinguish between these two concepts. And also, as I said, there is also B infinite word, which is in this case a mapping between integers, between all integers and into the alphabet, and it is presented as a sequence which is going to the infinite, to the infinity of on both sides. Yeah, I guess there is nothing really new for you, but just to be sure, I presented these definitions. So now we are ready to present the essential concept of the paper. It's the alpha power of a non-empty finite word. So basically, it's a repetition of the non-empty word R several times, depending on the alpha. And also, at the end of the repetitions, there is a prefix of the word R. So it means the alpha power. The alpha is not, in general, it is not an integer. It may be a rational number. In this definition, I defined that alpha can be bigger than 0. Commonly, we are considering only alpha bigger than 1 or equal to 1, but for the definition, it works also with the alpha smaller than 1. So I present it in this way, but I don't recall any paper which is considering alpha smaller than 1. So yeah, so basically power means a repetition. In many papers, only integer values of the alpha are considered, but for my paper, for my results, I repeat, alpha can be also a rational number. It means at the end of the repetitions, there is a prefix of the word R, which may be also empty, in which case the alpha would be an integer, a positive integer. yeah, it is somehow it is necessary to understand this definition because it is what the results of the paper is about. So I hope the definition is clear. So I will continue. If you have any question, you can just interrupt me because maybe this is good to say because I don't see the chat. So if you have any questions, either you can save the questions for the end of the talk, or you can just stop me and interrupt me. So here's some simple example. The first example for the power with the integer value of alpha, and the second example for the rational value. So it means that, as I said, at the end, there is a prefix 1, 2, 3 from the word 1, 2, 3, 4. I think is the example. The idea should be clear. So I continue. So let W be a finite or infinite word. I define the set theta with the parameter W, and it is the set of all couples R alpha, such that R to alpha is a factor of W. Yeah, R is also non-empty word, and alpha is a positive rational number. So I continue. And now we say that the word W is a alpha power 3 if the set, if the set as it is presented below, if if I consider the set theta such that or alpha are bigger or equal to alpha, and if this set is empty, then I say, or we say, that the word W is alpha power 3. Also, we define a concept of alpha to plus power 3. And there is this small difference that I say that the beta must be bigger, strictly bigger than alpha. Comparing to the previous definition, there I allow that beta can be equal to alpha. This distinction is important, and in some papers you will find this notion even with this notation. This is not my notation. I used it from some other papers. So this concept, this notation is used, and depending if we consider just alpha power 3 or alpha to plus power 3, we get different results. So I hope this distinction is clear. So we defined alpha power, and now we defined alpha power 3 words. As I said, this is also pay attention in some papers. If there is stated alpha power 3, sometimes it means also alpha with plus. So take care about what it exactly says. There are some famous examples of power 3 words, especially the square 3 words, overlap 3, and cube 3. Using the definition that I presented, these are the 2 power 3, 2 plus power 3, and 3 power 3. Examples. Also it is easy to see that alpha power 3 form a factorial language. It means that all factors of alpha power 3 word are also alpha power 3. This is, of course, in general, this is not true for any language, but for the language of alpha power 3 words, this is true. So this is some obvious but very useful in some proofs to be aware of it. Also it is easy to see that the reverse function preserves the power 3-ness. So for example, as I presented a couple of minutes ago, the right infinite word, if I just change the direction, if I make a reverse of it, I get left infinite word, and I can be sure that it has the same alpha power free properties as the previous, as the original right infinite word. So the reverse function, just changing the direction of the word, doesn't change the power freeness. Yeah, also easy to see, but yeah, it's useful to keep it in mind. Yeah, the results concerning power-free words are quite old, like more than 100 years. I would say the first very interesting paper concerning this concept was this paper from Alex Tew, with the German name über unendliche Zeichenreihen. Yeah, and in this paper, Alex Tew proved an existence of an infinite square free word on an alphabet with 3 letters. It is easy to prove that there is no infinite square free word on an alphabet with 2 letters. This can be proved very, very easily. But for the alphabet with 3 letters, it was not so obvious. And Alex Tew proved the existence, and he constructed such infinite square free word with using 3 letters. So this paper and this result is considered like kind of a breakthrough in this field of power freeness and combinatorics on words. So this is this important paper, and also you can see it is more than 100 years old. So the concept is quite old. As such, there are many results, many different generalizations of this. So quite naturally, there are generalizations concerning the alpha and also the size of the alphabet, but there are also some other generalizations. For example, there are abelian powers, pseudo squares, and reverse powers. I'm not sure if I would be able right now to present the exact definitions of these concepts, but I have seen some papers dealing with these concepts. Yeah, basically it's like that. I do not consider just repetition of the word. I'm considering repetition, but I apply also some function of the word before I repeat it. So it gives me some really many different combinations and possibilities how to generalize the power. Yeah, so many results, many papers, quite interesting field of the combinatorics. Okay, now I define the repetition threshold for some natural number k. So if I have a natural number k, I define that repetition threshold of this integer k is the infimum of all rational numbers alpha, such that there exists an infinite alpha power free word over an alphabet with k letters. Yeah, so basically, if I have the k represents the size of the alphabet, so I'm asking what is the minimal alpha, what is the minimum of the alpha, such that I can construct alpha power free infinite word on this alphabet. So this is called repetition threshold. This is not my concept. This is also from other papers. And why I present it is because of this famous Desjans conjecture that has been presented in 1972. So it's quite old. And Desjans conjectured these values for the repetition threshold. Yeah, this is I present this conjecture because I will use these results in my papers. These are like important to be able to prove what I proved. Okay, so this conjecture in the conjecture is currently proved. It has been proved by many different papers. No, just for the different configurations. If I say configuration, I mean like the combination of the size of the alphabet and the alpha. So depending on the configuration, different authors proved prove this conjecture for this configuration. The last step, the final piece of the puzzle, has been published in 2011 in this paper of Kari and Rampersad. Yeah, so the conjecture is proved, and I use the result, use this conjecture, use this, or actually now we can say theorem, it's no more conjecture. So I use this theorem, this result in my papers. I continue. Yeah, the obvious result of the De Jong conjecture is that there are infinitely many different finite alpha power free words over the alphabet with key letters on condition that the alpha is bigger than the repetition threshold. Yeah. So now we are coming to the open problems that I tried to solve, and I solved partially. So even if the concept of power-free words are quite old, there are still some long-standing open questions. Despite the effort of many mathematicians, there are some long-standing open problems that are of interest and that are not solved. So the Restivo and Salemi presented five of them. I will show you all of them. They are quite natural. There is nothing artificial, nothing complicated. These are quite problems that can be formulated in a very simple way. So if I have an alpha power free word u and then the positive integer n, I want to know if there are words w and v of the length n such that they can be concatenated with the alpha power free word u in such a way, and the result must be also alpha power free. So basically it's about extension of the word u in such a way that the resulting word has some given length and is still alpha power free. Yeah, and it's interesting in both directions, right, left, and also both of them simultaneously. So this is the first problem, which is still open. The second problem, given an alpha power free word u, construct, if it exists, an infinite alpha power free word having u as a prefix. So this is about infinite extension of the word u in such a way that the infinite extension, that the infinite word is alpha power free. In this case, yeah, here it is not explicitly stated if right or left infinite word is meant or be infinite. So as I said at the beginning, yeah, right and left, it is basically the same result, but it's a difference. There is a significant difference if we consider right or be infinite words. So in this problem, it is not explicitly stated which one is meant, but for all of them, it is in general, it is open, still open. Problem 3. Yeah, given an arbitrary positive integer k, does there exist an alpha power free word u such that this is about I'm looking for the maximal extension of the word u in such a way that there is no longer extension of the word u that is alpha power 3. So this concerns the words. So if we consider the words that are not extendable into the infinity, we are looking for the maximal extension of them. This is what the problem 3 is about. Now we are coming to the problem 4. Given finite alpha power 3 words u and v, decide whether there is a transition word w such that u, w, v. Okay, sorry, here is a typo mistake. There should be u, w, v is alpha power 3. So in this case, we are looking for a concatenation of two alpha power 3 words. So the question is if they can be concatenated in such a way that the result, that the concatenation is still alpha power 3. And the problem 5, the last problem, given finite alpha power 3 words u and v, find a transition word w if it exists. So yeah, this concerns the problem 4. The problem 4 is about existence. The problem 5 is about a concrete example of such concatenation, of such transition word. So as I said, these are 5 problems that are quite natural. These are quite problems that are really of interest if we are dealing with alpha power 3 words. And as you have seen at the beginning, there was the paper. They have been presented in 1985. So and still they are open. So I have tried. Okay, and then in the okay, so what was the state of the solution in 2019? In the paper of Petrova and Schur, there was a solution. There was a solution presented for the problem 4 and 5 for the cube free words. Also, there was some summary of the other results concerning these problems, and there we can find that problem 4 and 5 have been solved for some overlap-free binary words. So this was the state, and in addition, in 2019, Schur and Petrova and Schur presented this result in this form. For every pair UV of cube-free words over an alphabet with k letters, if U can be infinitely extended to the right and V can be infinitely extended to the left, respecting the cube freeness property, there exists a transition word W over the same alphabet such that UW V is cube free. So this was the result of Petrova and Schur. This is the answer to the problem 4. You can notice in the result that the condition for this result is this extendability, this infinite extendability of the words U and V. So this is kind of a premise. So we are supposing the words UV can be infinitely extended to right and to left, respectively. Concerning the extendability, these are the first 3 problems. It is not solved. Yeah. So you can ask how can we recognize that the word U can be infinitely extended? So for this question, we have no answer. But on the supposition the word U can be infinitely extended, we have this result. We can prove, or it has been proved, that there is a transition word W. So this is the result from 2019. And in the sense of this result, in the spirit of this result, with this suppositions, I have presented my results in 2020. Okay, but before I come to my results, I will show you also this paper of Schur from 2019. 9. And in this paper, Schur presented the following conjecture. Let L be a power-free language, and let IL, a sub-language of the language L, be the set of words of L that can be extended to a B infinite word respecting the given power freeness. Yeah, and Schur conjectured that if the words U and V are from this sublanguage IL, then there is a transition word W such that the concatenation UWV is from this sublanguage EL. So this is the conjecture of Schur. So if you compare it with this, with the problems of Restivo Salemi, here Schur considers explicitly B infinite power-free words. In the problem 4, so this is one difference. In the second difference, comparing seeing the problem 4. The problem 4 was also about finding the transition word, but here in this case, there is the additional requirement that the concatenation itself must be also extendable to infinity on both sides. In the problems of Restivo Salemi, in the problem 4, this requirement was not there. It was just about finding the transition word in such a way that the concatenation is power-free. But here we have the additional requirement that this concatenation must be extendable to infinity on both sides. Means to be infinite power-free word. Yeah. And actually, the main purpose of this presentation is to present my result concerning this conjecture, because I claim I have solved this conjecture for some configurations that has been stated in the name of the presentation. But before I will come to this concrete result, I will present my previous results because they are necessary. These are like the basic, the essential results that I have used to prove this conjecture for the given configurations. Yeah. So as a summary, we have these open problems from Restivo and Salemi, and we have this conjecture. Okay, there is also this paper from Shally and Schur from 2019. And the conjecture that I just presented appeared again in this paper. Sorry, there should be in 2019 instead of 2018. Yeah, but the only difference was that in this paper, the authors defined so-called Restivo Salemi property. So this is also the reason that I use this Restivo Salemi property in the name of my paper. So basically, Restivo Salemi properties are the conditions that are present in the conjecture. It means that the words, in this conjecture, it means that the words can be concatenated using some transition word, and this concatenation can be extended to infinity. So if the language has this property, then we say the language has the Restivo Salemi property. Yeah. So the conjecture has been presented twice, in 2 different versions. Okay, so we have these open problems and the conjecture. Let's go on. Okay, so now we come to my results. So first paper that I published concerning these open problems was the paper presented, published in the conference Developments in Language Theory in 2020. It was in the time of the lockdown and the time of the COVID. So the conference, the offline version of the conference, the meeting in person, has been cancelled. However, the papers still have been published as usual. And as it is clear from the name of the paper, I proved my results for the configurations alpha bigger than 2 and k bigger than 3. More or less, I will precise this result because yes, exactly. So here is this definition of the set upsilon. So yeah, it looks a bit complicated, but it's not that complicated if you spend some time with it. This is just because as I define the concept of the alpha power and alpha plus power, my results are different depending if we consider alpha or alpha plus. So because of this, I need to state this bit complicated definition. Yeah, I think it's not, maybe for the moment, it's not necessary to go into the details, just basically results hold for the alphabets bigger than 3. So the alphabets that have more than 3 letters. And for alpha power 3 words with alpha bigger than 2. If you abort this border 3 and 2, you need to look carefully if the results hold or not. Because depending if you have alpha plus or just alpha, it may be that the result does not hold for this configuration. So this is this is just what I have explained. Yeah, and as I said, in the spirit of the result of Petrova and Schur, I presented the following result. So given the configuration from the set upsilon, this combination of alpha and k, for every pair u and v of alpha power 3 words over an alphabet with k letters, if u can be infinitely extended to the right and v can be infinitely extended to the left, respecting the alpha power freeness property, that is missing the word power, then there exists a transition word w over the same alphabet such that u w is alpha power 3. Also, I have shown how to construct this word w. So for the given configurations from the set upsilon, I've proved I solved the problems 4 and 5 of Restivo and Salemi. Yeah, so now the question, basically what I want to present is how I solved it, or at least the very basic ideas. Okay, yeah, let's formally set, the problems 4 and 5 have been solved for a wide variety of powerful languages. Okay, so what is unfortunately the proof is quite technical. It's not an easy reading. Yeah, some attention and carefulness must be invested. But still I will present the very basic idea. It is this one. If I have two alpha power 3 words, u and v, and a letter x, such that the letter x is not a factor of the words u and v, then obviously the concatenation u(v) is alpha power 3 on condition that alpha is bigger than 2. Yeah, this is easy to be seen. Just consider if I have some factor in this concatenation which contain x and which is a square, then the letter x must appear twice, at least twice. And if the x has just one single occurrence in the concatenation, then there cannot be such a factor. So means the letter x in this case works like a border between two problems. I can solve the two different problems for the u and for the v. And if the words u and v are power free, I can just concatenate them using the letter X, and I'm sure that the concatenation is still alpha power free. Yeah, this is the very, very basic idea. Yeah, of course, practically then the proof is much more complicated. But here I want to emphasize one more thing, because in this case of the concatenation UXV, basically I have to prove for every vector containing X that this vector is alpha power free. But as I explained, in the case of one single occurrence of the letter X, this is trivial. This is clear. But what I'm doing in the proof, I'm considering a bunch of the occurrences of the letter X. I'm using some finite number of occurrences of the letter X instead of one single occurrence. So this is the generalization of this idea that I used and that allowed me to prove my result. So what is the difference concerning regarding this very basic idea? Yeah, the difference is fortunately the difference is not that huge, because if you consider some vector which is sufficiently long and which contains some occurrence of the letter X, and then you can easily show that sufficiently long factors are still square free, because if you want that the vector is not square free, then you need to repeat the bunch of the occurrences of the letter X. There is some location, there's some finite vector which contains all the occurrences of the letter X, and this bunch of these occurrences needs to be repeated, and it is not repeated. So principally, it is like in the case of the single occurrence of the letter X, but additionally, you need to, so for the long vectors, it is easy. The idea is the same. You just need to take care about the short vectors that are located in the neighborhood of these occurrences of the letter X. Yeah, as I said, there are then in the proofs, there are some many technical details, some careful observations of some distances between the occurrences of the letter X and so on. Yeah, I will not step into the details of the proof. I just wanted you to understand the basic concept of the proof. Yeah, okay. So as I said, I consider finite number of occurrences instead of a single one. And I wanted, yeah, also this explains also why do I need, I will come back, regarding this very basic idea. This explains why I need the Dejean conjecture, the Dejean theorem, the results that I just presented. Because so if I have some alpha size k, I need one letter of this alphabet to be this special letter, which is only finite number of occurrences. And the rest of the infinite word is basically an infinite word on an alphabet of smaller size, of the size k minus 1. So I somehow need to know for the k if it is even possible to have some infinite word, infinite alpha power free word on an alphabet of smaller size. So for this reason, I used the Dejean conjecture, which gave me the exact results that I needed, and also the Dejean conjecture set the boundaries on my results. This is, for example, this is the reason that my results hold for the only for the configuration with alphabet which has more than 3 letters or three letters, because if I have 3 letters and if I reserve 1 letter for this special letter X, then there remain only 2 letters. And with 2 letters, I can construct infinite alpha power of words on condition that the alpha is strictly bigger than 2. This is the alpha plus bigger than 2. So for example, this is the explanation for the boundary of my result. Yeah, and also this is the reason that my result does not apply for the binary alphabet, because in the binary alphabet, if I reserve one letter for these finite occurrences, then then I can prove nothing. The rest is just an infinite word on one letter, and this is, of course, not of interest. So I used the Dejean conjecture, and it defined the boundaries for my results. Yeah. Okay. So a little bit of more details from the proof from the paper of 2020. What I needed is if I have some infinite word with some factor w, then I have constructed another infinite alpha power 3 word with the same factor, containing the factor w, and also the infinite word has only finite number of occurrences of some letter x. So this is the very basic result that I needed for all the consequent results that I have. And on the other hand, having this result, the others were more or less simple or obvious. Yeah, it depends. So this is the crucial construction. I have infinite alpha power of reward having some factor w, and I construct another alpha power 3 infinite word having the same factor, but having only finite number of occurrences of the letter x. Yeah, the proof is considering some infinite word on the alphabet of smaller size, and then I'm looking for some common factors of these both infinite words, and depending if there are infinitely many of common factors or just finitely many, I'm looking for some proper location where I can join these two infinite words together, to cut them and join them together. Yeah, as I said, this stuff is very technical. I will skip the details, but this result is the essence, just to reduce the number of occurrences of the letter x from the infinite number to the finite number. Yeah, and then using this, and then when I had these two infinite words, both of them with finite number of occurrences of the letter x, I found some other way how to join them together, how to cut them and concatenate to find the transition word. But it was then more or less easy. Yeah. So this is the result that I presented in 2020. Then in the last year, on this conference, descriptional complexity of formal systems, I presented another result, which was an extension of the previous result. Yeah, in the first paper from 2020, I was considering only one-sided infinite words. But to be able to abort the conjecture of sure, I needed to generalize my results for B infinite words. So it was the aim of this paper. And then the last result that I obtained, that I written, is this one. This is currently the last paper. This is for the moment. This is not published. This can be found on the archive for the moment. But I suppose it will be published there. I think there is no mistake. It is just applying of the ideas from the previous paper. We can say that the last paper on the archive is kind of a cherry on the cake, because the most difficult parts of the ideas and the proofs have already been published in the previous 2 papers. And this is, yeah, that's really just cherry on the cake. So in the paper, because yeah, I presented both these 2 papers together on this slide because they are using the same notation, and they are quite yeah, they are actually, it could be just one paper. It is using the second paper are using the results from the previous paper extensively. So anyway, in these 2 papers, I defined this set upsilon with tilde, and this is the set of the configurations for those I proved the conjecture. If you compare it with the previous set upsilon that I defined on the previous slides, this one is a subset, strict subset. This is, for example, the reduction can be seen in the alpha. In the previous configurations, I proved the results for the alpha bigger than 2. In this case, I had to reduce alpha to 5. So means that considering the B infinite words brought some difficulties, some challenges that I wasn't able to cope with, and to be able to prove at least something, I had to consider just powers bigger than 5. But I feel there is a space for improvement. I think the proofs could be generalized. I think I will be able to. So for the moment, I published it in this way for the alpha bigger than 5. I think it is still good because the conjecture is like 15 years old and there is no better result. So I think it is still publishable. So for these configurations from the set upsilon with tilde, I proved the conjecture of Schur from 2009. But currently it is just on the archive. It is not reviewed and published. Yeah, the last papers are also very technical, and in addition there is a lot of notation, because for every language I need to distinguish between B infinite word, between left infinite, right infinite, between the size of the alphabet, because I'm skipping between the sizes of the alphabet depending if I consider just the occurrence of the letter X or just words without this occurrence. So you will in the papers you will see a lot of notations like this on the slide with many indexes, so it makes it a bit more complicated to read, but I found no better way how to do it, because I need all these indexes, and for every variable it needs to be stated what is considered in question. So I define these sets of B infinite, left infinite, right infinite words. Yeah, and basically in the first paper that has been published last year in the DCFS, I generalized the concept that the result that I just presented for B infinite word. So now I'm considering a B infinite alpha power 3 word with some factor, and I construct another B infinite alpha power 3 word with the same factor and with only finite number of occurrences of some letter X. So in the paper from the last year, I generalized this basic essential result, and I showed it for this configuration. This is possible to construct such infinite words. It is possible to restrict the number of occurrences of some letter X. So this is the result from the last year. Yes, this is basically the consequence of the De Jean conjecture. So, yeah, as I said a couple of minutes ago, this defines the boundaries of my results. Yeah, here is basically what I just said, but using a lot of notation. I'm just realizing I did not define many of the concepts. For example, suf is the set of suffixes, f is set of factors with the index rec. It is the recurrent factors, but I think it's too technical. I just skip it. No, I will not bother you with these technical details. I think basically I explained everything what I wanted. The last slides that I'm just skipping show the same, but using the notation that I'm using in the paper, so you can get the feeling of the paper. It's yeah. Okay, I think I stop here and I give the word back to the Narat.
Thank you very much, Josef. Does anyone have any questions? Oh yeah, Gabriele.
Hi.
Hello.
Hello. My question is about the length of W. Do you have any bound?
Yeah, it depends. As I consider the finite number of occurrences of the letter X, it is depending on the lengths between the occurrences. It is the span. It is the if you consider the maximal factor, which have X as a prefix and X as a suffix, then this length is determining the length of the transition word. And also, as I remember, I said that I'm considering the common factors of the infinite word with the infinite number of occurrences of the letter X and the word without the occurrence of the letter X, and I'm looking for the common factors. And then it may happen that there is only finite number of common factors, and then the maximal length of this common factor is also determining for the size. So I don't know. So it may be arbitrarily long. Yeah, there is no upper bound. I think it can be arbitrarily long.
Yeah, of course. I was interested in a lower bound.
I think no. For the moment, I see no way how to restrict it. There you would need to find some another trick, some another observation. Using my result that I had, there is no obvious consequence that could restrict this length.
Okay. Thank you.
You're welcome.
Are there any other questions?
I have not a question, but just Josef, could you please send me your slides after the talk? I will put them online. Thank you.
Okay, I will send it today.
Thank you.
You're welcome.
So the class is not here. It was just possible. Sorry.
All right. Yeah, if there are no other questions, thank you again, Josef.